We're going to go ahead and title this lecture here. This is Math in Chemistry. Kind of some background math concepts that we need to be able to perform calculations in this course. Okay, as I'd kind of previewed, and I think a lot of people have heard this word before, we'll talk a lot about sig figs. But actually, the first thing I want to do is just make sure we're all on the same page with what's called scientific notation. Okay. Scientific notation is just another way to represent numbers. And you can do it for literally any number. Any number you can think of, you can represent in scientific notation. All right. However, it's most convenient for numbers that are either really large or really small. Okay, one of the downsides of writing these notes as I go is that I'm a terrible speller. So if I make a spelling mistake, you know what I mean, all right? Roll with it, okay? But yes, we're going to use this most conveniently to represent numbers that are very large or very small. So what do I mean? So first of all, most of the time when we're looking at a number, it's in what's called standard notation. All right. The problem is let's say that I wanted to represent, for example, how many water molecules there are in my water bottle right here, all right? In chemistry, molecules are so teeny tiny small. If I wanted to approximate about how many water molecules there are in that water bottle, it's something on the order of somewhere in there. Okay, that's a very large number. And as you can tell by that pause, it took me a really long time to write that number. If I was doing a calculation and all of my intermediate steps involved a number that was that big, it would be a really big pain in the butt, and it'd be really easy to make a mistake. Accidentally leave off a zero, add an extra zero, whatever it may be. So this would be this number in standard notation. I could represent the same number in scientific notation as 1 times 10 to the 24. Okay? These, importantly, what we want to note is that these are the exact same number. If you were doing a calculation and you entered in your number in standard notation into your calculator, you would get the same answer as if you entered your number in scientific notation. There's no difference in the value of these numbers. They're just represented differently. And as you can see, just by how little writing I had to do, scientific notation was very convenient here. Okay? So, first of all, we'll do some examples. What we're going to do is a bunch of examples converting from standard to scientific and back again, all right? But let's first just talk about what we call, proper scientific notation. Okay? So if we do proper scientific notation here, let me just put down an example and then we'll pick apart what makes this proper scientific notation. Something like 3.25 times 10 to the third. Okay? Importantly, how do I know this is proper scientific notation? I can only have one digit to the left of the decimal. All right, you're allowed to have one digit in the ones place here of your decimal. You can't have any more than that. So just one digit to the left of the decimal. We can have any amount of digits afterwards. Okay. You will also always see times 10 to the. That will always be in scientific notation. In theory, you could use other bases if you want, but they're way less convenient. We like to use 10. There's something convenient about it. So we're always going to use this base of 10 in our scientific notation, and then times 10 to some power here. All right, so times 10 to some power. All right, that would be proper scientific notation. All right, to be clear, from a math standpoint, this would be the same thing as 32.5 times 10 squared. Those are the same number from a math perspective, but this is not proper scientific notation. What makes this not proper? I got more than one digit to the left of that decimal, right? We can only have one digit to the left of the decimal. We can't have two or more. All right, that's what we call proper scientific notation. Okay, so now let's jump in and out. All right, now we're going to worry about how we convert from standard to scientific, or vice versa. All right. So first of all, what I think might be helpful before we get going, again, we always have times 10 to the here. So what exactly is this doing for us in this number? All right, let's just make a little cheat sheet here where we're going to put 10 to some power. I'm going to put 10 to the 0 in the middle here. All right, and then we'll talk about what number that is down below. All right, so let's do a few examples. Let's do 10 to the 0, 10 to the 1, 10 squared, and 10 to the third here. All right, we got some math brilliance here. What is 10 to the 0? 1, right? Anything to the power of 0 just has that value of 1. Okay, and then what would 10 to the 1 be? 10, anything to the power of 1 is just itself. What's 10 squared? 10 times 10, that would be 100. And what is 10 cubed? 10 times 10 times 10, so now we got 1,000. So notice how in each of these here, when we're increasing this exponent by a value of 1, that has an effect of adding a 0 onto the end of this number here, right? Representing a bigger and bigger number depending on how big that exponent is. So just going back to the top here, comparing these two here, 10 to the 24 and 10 to the 3, which one's a bigger number? 10 to the 24 by quite a lot, right? 21 orders of magnitude, a lot bigger, okay? So yes, as that exponent goes, we get a bigger and bigger number, okay? Now, we don't have to use positive exponents, though. We can also use negative exponents. So now what if we do 10 to the negative 1, 10 to the negative 2, 10 to the negative 3? All right? So strictly speaking, if we have a negative exponent, that means that we have, I'm going to do this the long way here, 1 over 10 to the 1, or 1 over 10 to the 2, 1 over 10 to the 3. All right? That's what a negative exponent is telling me. And if we evaluate that, what is 1 divided by 10? All right, I'm going to actually try to keep these on the same line here. 1 divided by 10 is 0.1. So then what do we think 10 to the negative 2 would be? 0.01. And what about 10 to the negative 3? 0.001. So now we're representing smaller and smaller numbers by adding zeros to the right of that decimal point. Okay? So this is kind of the first step in terms of jumping in and out of scientific notation, is taking a step back and being like, wait, do I have a big number or do I have a little number? Should I be using a positive exponent or a negative exponent? All right, so let's now work on our converting here. we're going to take 10, we're going to do 3 point, what did I say before? Let's just do that one. 3.25 times 10 to the 3. All right. This number here is in proper scientific notation. I'm going to convert it into standard notation. Okay. And what I'm going to do is I'm going to have to move that decimal point. I'm going to have to move that decimal point a total of 3 times. How do I know it's 3? Because that's what my exponent is. So this is telling you how many jumps you're going to make here. And we're going to move that decimal point 1, 2, 3 positions over. Okay, so this would give us 3,250 here. Notice I have to add in that 0 because I made this extra jump here to the end of my number. All right. Now, what if I wanted to do, let's say 1.7 times 10 to the negative 2? All right, well, I'm again going to have to jump my decimal point. How many times am I going to jump my decimal point? 2, because again here, the difference is I'm going to jump in the other direction. Now this is a small number because it's a negative decimal, a negative exponent. So I'm going to go 1, 2, and so this is going to leave me with 0.017 in standard notation. Okay, again, I got to insert this 0 here. This is where my decimal is. I like to write my numbers with a 0 out front because that's considered kind of proper and fancy, but nonetheless here. So that's how we get this 0.017. Okay, now, how do I know to jump to the left in one case and to the right in another case? Rather than trying to memorize, oh, it's left here and right here, again, just go back to, do we have a big number or do we have a little number? Right? If I look at 3.25 times 10 to the 3, I want to look at 10 to the 3 and ask myself, is this a big number or a little number? Meaning, is it bigger than 1 or less than 1? 10 to the 3, what do we think? It's a big number, right? So that's how I know I need to jump in this direction here to give me a big number on the other side. Right? Likewise, here I have a negative exponent. So that should be a little number. That's how I know I have to jump in this direction so that I have a little number at the end of the day. So I don't want you trying to memorize left and right. That's a very easy way to get things switched around. You're smarter than that, right? We can take a step back and look at this number and say, what's going to make sense? All right, let me just say, that's the difference between people who are pretty good at chemistry and people who are rock stars at chemistry, is being able to do a calculation and look at the number at the end and say, that number makes sense. Right? A lot of people remember the steps. They can punch it into their calculator. And then they get to the other side and it's like a black box. And they're like, all right, hope that's right. If you can look at that number and you're like, that number makes sense, that's how you're going to be like extra special good. What we call like sanity checks, right? Make sure that's a reasonable value based on what your expectations are. Okay? So now we're going to go the other way. Let's say 145 here. And I want to convert this into scientific notation. So first of all, I know it's going to look something like this. Something dot something times 10 to the something. Okay? So first of all, help me fill it in here. What's going to go out front of the decimal? That 1. I'm only allowed 1 digit out front, so the only thing I can put there is that 1. And that means the 0.45 has to go on the other side. But now the question is, what's that exponent going to be? All right. And again, we can try to memorize left and right, but we don't want to do that. Instead, we want to look and say, is this a big number or a little number? It's a big number. So should we have a positive exponent or a negative exponent? Positive. Okay, great. So now all of a sudden, all we got to do is figure out what the value is. Again, we're going to jump. Here's where my decimal is located. 1, 2. This is 10 to the positive 2, or we can just say 2. Okay? So again, don't try to memorize left and right in terms of how you're jumping. Memorize, or rather, don't memorize. Convince yourself, big number, little number, all right? That's the way that you want to do this. So then let's just take this, finish this example off here. I want everybody to take a second and convert this number here into scientific notation for me? All right, so something, point something, times 10 to the something. All right, what's going to go in front of my decimal? That 5. What's going to go on the other side of that decimal? 7. That's 7, and times 10 to the... Awesome. Okay, so first of all, big number, little number. It's a little number. So that's how I know I'm going to need a negative sign out front here. And then the question is just what value is that negative number? We're going to bounce this 1, 2, 3 to put it in the correct position here. So times 10 to the negative 3. Okay? When you're practicing, you can convince yourself that these numbers are the same by punching this into your calculator here. It will give you that 145. Right, that 145. For larger numbers, 1 times 10 to the negative 24, your calculator is just going to spit it back out in scientific notation. It's going to be like, that's way too many characters. Here it is back in scientific notation. When we start doing problems that involve really big or little numbers, I'll teach you how to use your calculator to toggle from one form to the other, because it can be more convenient representing in one form or the other depending on what type of calculation we're doing. Okay? Every calculator has the ability to jump between both. Cool. All right. Any questions on scientific notation before we get going here? Cool. All right. So now everybody's absolute favorite topic in all of chemistry here, significant figures. Okay, we're going to, general chemistry, especially 1A, is very calculation heavy. We do a lot of calculations. They tend to adopt the same form, what we call dimensional analysis, but nonetheless, and in every calculation that we're going to do, we're going to have the punch it in your calculator step, get the answer, but then you're also going to have to report your answer to the correct number of sig figs. So these sig fig rules that we're going to lay out here are something we're going to do over and over and over again. We want to make sure that we have that base information down, because we're just going to build off of that with pretty much every analysis that we do. All right? So first of all, the question that we want to answer is, why the heck do we have to worry about sig figs here? Like, what are sig figs? Why are they a thing in a chemistry course? Why do we bother? All right. A lot of you have done a lot of math courses before, and you've never heard the word sig figs, right? So what's the deal? There's a big difference between how numbers are treated in math versus science. All right. In math, numbers are what are called symbolic. They don't correspond to anything concrete other than that symbol of being 2, which is the same as 1 plus 1, which is the same as 2 times 1, whatever it is. They're these symbolic entities. They're not necessarily tied to real world things, all right? In science, and again, specifically in chemistry, numbers are not just symbolic. Numbers correspond to measurements. All right, so we would never just say 2. You're never just going to have 2 floating around by itself. It's 2 grams or 2 centimeters or 2 liters. It always corresponds to some measured value. And we'll talk about what those units mean next class period. We got a bunch of different units depending on what it is we're trying to keep track of. But that's the big difference, is we're not just doing this math for the sake of doing math, right? We're doing them to analyze some measurements. Okay? Because of that, we have these rules of how many digits we use to represent those measurements. All right? So first of all, if you were taking a math course, 6.0 would be the exact same thing as 6.0000. Those are identical in a math class. All right? Probably wouldn't even include the 0.0 on the end there. All right? They have the same value. You punch them into your calculator. It's the same number. all right? But if we're talking about a science class and all of a sudden these are measurements, if we report a measurement of 6.0 centimeters, this is not the same thing as 6.000 centimeters. All right, first of all, these are measurements, so we got units on them. You'll hear me say we never have naked numbers in chemistry. They always got units associated with them. All right, and because we're talking about measurements, all of a sudden, these are not the same. They do have the same value, right? So from a calculation standpoint, they're interchangeable. But when we add these extra digits onto our measurements, we're saying something about how precise that measurement is. All right, so the number of digits here, these extra digits, imply a more precise measurement. And the last thing you want to do in science is over-represent your precision. Right? You're not going to publish a paper with a value in it and pretend like you knew that number to 15 digits when really you only know it to 2. That'd be a great sin in all of science. We're very careful to make sure to represent how precise we know a calculation to be by displaying a certain number of digits. Okay? So that's this whole sig fig business, is making sure that we're bookkeeping how precise we've been in our experiment and making sure we're not over-representing that precision. Okay, when we say 6.0 centimeters, all right, that means that this is somewhere between 5.9 and 6.1, somewhere in there, right? Whereas when we say 6.000 centimeters, now all of a sudden this is between 5.999 and 6.001, a much smaller range. Again, indicating a higher degree of confidence of that measurement. I know this is much closer to that value of 6.0 than this one is here, right? I'm more confident about this measurement than I am about this one. And again, it has everything to do with the amount of digits that are displayed, what we call significant figures. Okay? So what we're going to do now is we're going to learn a bunch of rules. We got to first learn some rules for how we count sig figs. And then we're going to learn how to round numbers to the correct number of sig figs. All right? These are going to be this set of rules that I lay out, and then you're going to apply them to a bunch of different examples. And that's kind of like par for the course in a chemistry class, in these introductory science courses. Here's a bunch of rules, go and apply them into these various situations. Okay? So again, our first thing that we need to learn how to do is we need to learn how to count significant figures. Okay? As I'm going through my notes, you'll notice that I title these different sections, right? That's to help you when you're going in your notes and you're like, oh crap, how do I go about counting sig figs? You can go back to that particular topic. Again, kind of just trying to make sure we organize our notes on our page in a way that's going to be most useful. Okay, so we have rules for counting sig figs. All right, let's lay them all out here. Rule 1, all non-zero digits are always significant. All right. So let's say that we have a measurement like 1.45 centimeters. And I'm trying to count how many sig figs there are in this number here. Well, all of these are non-zero digits, which means that all of them are considered to be significant, right? So in this measurement here, I have a total of 3 sig figs. I'm going to be lazy and just say SF. Okay? Now, I should be good and put units on all of these examples that we're going to be doing, but we haven't covered units yet, so for the sake of simplicity, I'm going to leave off these units. But remember, if we're talking about sig figs, we are talking about measurements. All right? So I'm going to put down a few examples, and you're just going to count the number of sig figs that you see for me. All right, again, the typical workflow, I'm going to go through some stuff. I'm going to put down some examples. You do them on your own, and then we'll work through them together, right? So the opportunity here, or rather the idea, is to give people the opportunity to try to apply that first rule to these two examples, and then in a minute, I'll go through and talk about them. Cool. All right, 136.2. How many sig figs we got? 4. 1, 2, 3, 4. All non-zero, all significant. 12. How many sig figs we got? 2. Cool. All right, so then clearly the pain in the butt part's going to be the zeros, right? Because if it's not 0, you know it's significant. So how do we deal with the zeros? All right, so rule 2. If we have a zeros between non-zero digits, they are also always significant. All right, so let's see if we can apply this rule. I'm going to put down examples. You guys try to count the number of sig figs here based on this rule. $14.03, what we got? 4 sig figs, right? So we have our 1, 2, and this 0 sandwiched between two non-zero digits is going to count. So we have 4 sig figs here. Clearly very creative because 10.42 also has 4 sig figs, right? 1, 2, 3, 4. How do I know to count this 0? Because it's between two non-zero digits, making it always significant. All right, so this one's also 4 sig figs. All right, so this next rule is going to apply to very small numbers. All right, what we call leading zeros. Leading zeros are never significant. All right, so again, what do I mean by a leading zero? Here I'm talking about a really tiny number, so something like 0.035. If I'm going to count my sig figs here, the leading zeros, the one out front here, are never going to count. So if I'm counting sig figs, I'm going to ignore 1, 2. All right, so we ignore those leading zeros. This has 2 significant figures. Okay? All right, so do these next 2 examples for me. All right, what do we think about that first one? 0.00382. 3 sig figs, because I'm going to ignore 1, 2, 3 sig figs. And what about this last one here? How many sig figs? 4, because again, I ignore the leading ones. 1. Why does this 0 count and this 0 count? Sandwiched between, right? So going back to rule 2, they're located between non-zero values. So all 4 of these count, or rather, those 4 count as sig figs. All right, so we got the ones out front, we got the ones in the middle. What about the ones at the end? All right, and this is kind of our biggest pain in the butt rule here, what we call our trailing zeros. They are significant if, big if here, there's a decimal in the number. Okay, so those trailing zeros are going to be a case-by-case basis, and it's going to be based on whether we see a decimal point located in that measurement. All right, so let me give you an example of one where they do count, and we'll do an example where they do not count. Okay, so those tailing zeros, the ones at the end of the number, they will count if there's a decimal in the number. So if I have something like 4.00 and I'm counting my sig figs here, I would have 1, 2, 3. I'm going to count these zeros because there's a decimal point explicitly represented in that number. All right, so here we have 3 sig figs. So then when wouldn't they count? This is going to be when we're talking about very large numbers. So for example, if I had 15,000, all right, we're looking at those trailing zeros and I'm asking myself, do they count as significant? Well, do we see a decimal point in that number? No, so then those trailing zeros don't count. This number here has only 1, 2 sig figs. Okay, so our trailing zeros, we're going to count them as significant if we have a decimal point located in that number. We're not going to count them if there's no decimal point in that number. All right? Cool. All right, so let's just practice this one real quick. I'll keep these examples up here. All right, 1.250, what do we got? 4. So we got 1, 2, 3. We get to a trailing zero and we ask ourselves, is it significant? Well, yeah, we got a decimal in that number. So this has 4 sig figs. What about 1 million? This one just has 1 sig fig because there is no decimal represented in that measurement, which means I don't get to count any of these zeros here as being significant. All right, 0.00305. I don't know why I did this example. It has no trailing zeros, but whatever. Just rolling with it, making sure we've got our practice down. How many sig figs do we see? 3. So I ignore these ones here because they're out front. And then I'm going to count this one in the middle there because it's between 2 non-zero values. All right, let's go to this last one here. How many sig figs do we see? So we've got all of our rules kind of rolled into one here. I ignore these leading zeros. They never count. I'm going to start here 1, count this one because it's sandwiched between, and then I'm also going to count these ones on the end because there is a decimal point in that number. okay? Cool. So skill number 1, we need to be able to count sig figs in our numbers, right? In our measurements. There is an exception, not really an exception because they don't count as measurements, but nonetheless, we have what we call a special case, which are these exact numbers. All right? Exact numbers are numbers that have an infinite amount of sig figs. Okay? And there's 2 special cases that we're going to see in this course of exact numbers. The first is anything that we count. All right? Remember that the whole purpose of these sig figs are to indicate a degree of confidence in how well you know that measurement. Well, if we're counting something, we actually know that quantity exactly. All right? So for example, we have 34 people in this room right now. Do we have maybe 33.9 or 34.1? Is it somewhere in there? No, it's 34. We don't got a random arm floating around in here somewhere. We have 34 people. That's an amount that we count, and thus we determine that to be exactly that number of people, right? A dozen eggs, 12 eggs. There isn't maybe 11.9 or 12.1 in there. They're not somewhere in there. No, there are 12 eggs in that carton, right? So those are things you count. So example would be 34 people or 12 eggs. These numbers, they look like they have 2 sig figs if you're applying our rules for sig figs. So context is really important. This isn't something that we measured, it's something that we counted. All right, so counts have an infinite number of sig figs. You know, the nice thing about things that have an infinite number of sig figs is they do not limit your sig figs in calculations. And that's kind of our next step, is talking about calculations and how to deal with sig figs. Well, if you have an exact number in there, you don't have to worry about it. All right. The other example that we see are what we call definitions, quantities that are defined relative to one another. Okay, and this kind of gives you a little bit of a preview into what we'll be talking about next class period with regard to unit conversions. But so for example, here in America, we're used to measuring distances lengths in, let's say if I was measuring the size of my phone, I would measure it in inches. If we were in Europe, we'd be instead measuring the size of our cell phone in centimeters. Well, you can convert freely from one set of units to the other, right? From one set of length measurements into another. And those conversions are defined. So for example, not anything you have to have memorized, but again, just an example here. 1 centimeter, or rather 1 inch, is defined as 2.54 centimeters. And that doesn't have any amount of wiggle room here. That's what it means to be an inch, is to be exactly 2.54 centimeters. So this conversion here, this definition, we would consider to have an infinite amount of sig figs, or to be an exact number. Even though it looks like this side has 1 and this side has 3, no, it's a definition, meaning that those numbers are exact. They won't limit our sig figs when we do our calculations. Okay? Okay. Cool, so we got our counting of sig figs down. The next skill that we need is we need to learn how to round numbers to a certain number of sig figs. Okay? So how do we round to a correct number of sig figs? What we're going to do is we're going to take an example here. We're going to do 3.234, and we're going to round to 3 sig figs. And I picked 3 completely arbitrarily. All right, just to do an example here, we're going to say 3 sig figs. There's going to be a logic behind how many we round to when we start doing calculations. But right now, I'm just arbitrarily picking and saying 3 sig figs. Okay, so what we need to do is we need to start counting and mark that 3rd sig fig in this number. All right, counting from left to right here, we have 1, 2, 3. This would be my 3rd sig fig. You're going to see this notation that I'm going to use over and over and over again in this course, where I keep track of my last sig fig by putting a little bar over it. All right, that means that that's the last sig fig in that number. And I need to round to that position there. Okay, so my rounded value here would be 3.23. Importantly, when we say round to a certain number of sig figs, that means our answer must display those 3, in this case, sig figs. All right, so 3.23, we're all convinced there's 3 sig figs there? Great, so then I rounded that number to 3 sig figs. Okay, now what we do is we're going to, so when we round, we got 2 different situations here. We could either round down, which is a little bit of a misnomer because it means that we keep the number the same. Okay, and that's if that next door neighbor, that next door digit is less than 5. So when I'm rounding a number, as in this case here, I'm going to look next door to that last sig fig, and I'm going to say, is that greater than 5 or less than 5? In this case, it's less than 5, so I round down, meaning I just keep that 3 as a 3. Okay? Or, so let's just do our example here, just to kind of have it. That example would be 3.234. where we marked that 3rd sig fig, 3.23. And again, we call it rounding down, even though we didn't change that number to 1 fewer. It's just a 3 still. Okay? Or we round up, meaning we increase that number by +1. And that's if that next door digit is greater than or equal to 5. Okay? So a good example would be if instead I had, let's say, 62.487, and I was going to round this to 3 sig figs here. Everybody take a second. Round this one for me. All right, what do we get? 62.6. Wonderful. All right, glad this is a bunch of review for us here. Importantly, you only ever look at the next door neighbor. So it wouldn't matter if, for example, in this first example, even if it was 3.234,99999, you only ever look at what's directly next door to do your rounding. I'm not going to round here and then keep on going or anything like that. It's only looking next door when you do your rounding. Okay, this would round to the exact same 3.23 when I did my, if I was rounding it to 3 sig figs. Cool. All right, so then let's just do some examples before we move on. You're going to, we'll stick with our same arbitrary 3 sig figs here. So examples. All right, 2.4782. First of all, what is my third significant digit? What's the value of that third sig fig?
7.
That's 7. So this is the position I'm going to round to here. Do I round up or down? I'm going to round up. So this becomes 2.48. One of the things that you're going to see me do that's a good habit to get into is we're going to put a box around our final answer. Boom, that's my final answer reported to the correct number of sig figs. On your exam, your final answer that you're reporting to your correct number of sig figs, you're going to put a little box around. That's how I know that's your final answer. All right, so you'll see me do that over and over again when we do our examples here. Okay. 0.0030643. What is my third sig fig in that number? What's the value of that third sig fig? The 6, right? I don't count these leading zeros. Those are not significant figures. So I'm starting counting here, which means it's that 6. Okay. Do I round up or down? In this case, I round down or keep it the same. 00306. All right. These next examples are a little bit weird. Okay, for 120, what's my third sig fig? That's 0? Okay, great. So, 120, I'm done. What's wrong with that? How many sig figs do we see in that number as represented? 2. And what did we say about if we're rounding to a certain number of sig figs? That means that our answer must display that number. I told you to round to 3 sig figs, and you're showing me an answer with only 2. That's not correct. This 0 at the end here, we want to indicate as being significant. So how do we do that? How do we make trailing numbers significant? The decimal. Now, I can't do this because now how many sig figs does it have? 4, and I only need 3. So what we're going to do is just put the decimal in there. Again, something you would never see in a math class is just a random decimal tacked onto the end of a whole number. But in chemistry, that decimal point means something. It's indicating that that ones place is significant. So you will see this notation here with that decimal at the end of that number just to indicate that that 0 is significant. Okay? Cool. And then the last example, this one's like a deceptively tough one, or rather one that students make mistakes on pretty easily. First of all, what's the third sig fig in this number? What's the value? That's 7. Is it going to round up or down? Okay, cool. So the biggest mistake that I see is students say, okay, 148. Boom. There's a problem here. And that is we very much so just changed the magnitude of that number. If I told you, let's read this number here. What is this number, like read out loud? 1,479,000. All right. If I told you I was going to give you $1,479,000 rounded to 3 sig figs, and I gave you $148, you'd be feeling pretty gypped out, right? That was a retirement amount of money, and now all of a sudden you can buy a nice pair of shoes. All right. We can't change the value or the magnitude of that number, which means that 1 still needs to be in the millions place. That 4 still needs to be in the 100,000s place, et cetera, et cetera. So we have to tack on those 1, 2, 3, 4 zeros onto the end here. Let me just line these up so we can see it a little bit easier. So we don't change the value of that number. Okay. So when you read it out loud, you still need to start with 1,400,000, whatever. Okay. Cool. So that's just a common mistake that people make is they drop off those zeros for large numbers. Make sure you're not changing the value of that number. Cool? All right. We got 2 more things to do here. 2 more skills that we need to learn how to do. And these are now incorporating operations into our discussion of sig figs. By that, I mean now we're going to actually start to do some math. All right? We got rules for what we call carrying sig figs. All right, so for example, in the lab, we go and we take a mass measurement by putting it on the balance. And then we take a volume measurement by reading off our graduated cylinder. And now we want to analyze that, do some math to figure out the density, the mass over volume, right? So we're going to take grams divided by milliliters. Well, now we need to figure out how to represent that answer to the correct number of sig figs, okay? So this is how we deal with these operations. We're going to break these into 2 categories here. All right, we have our multiplication division. And then our other bucket of rules are for addition and subtraction. And we're going to put these up at the top just to remind ourselves that these are different rules. All right, the number one mistake that people make when they're doing sig figs is to apply the rules for a multiplication and addition to for multiplication division to an addition subtraction problem, right? The rules are going to depend on what your operation is. So we got to first pay attention to what operation it is, then we apply those rules, okay? So the easier of the two are our multiplication division rules. So let's go through those first. Okay. So first of all, what I'm going to do is I'm going to put an example down here, and I'm going to leave some room for listing these rules up at the top here. But let's just kind of get an example down so we can see what's up here. Let's do 2.67 times 1.3. All right, step one, just do the math. Punch it into your calculator, figure out what your answer is, all right? And all these calculations that we learn how to do, most of the points are going to be designated towards if you got the right answer. There's always going to be that one extra point that's going to be if you reported it to the correct number of sig figs. But get the calculation first. That's the most important thing. So I'm going to punch into my calculator 2.67 times 1.3, and it's going to spit out 3.471. All right, but now I need to report this answer. I'm not going to put a box around it yet because I'm not done with it. I need to report that answer to the correct number of sig figs. And for multiplication and division, what we're going to do is we're going to count the number of sig figs in each of our inputs. All right, what do I mean by my inputs? What's an example of an input in this calculation? The 2.67. What's my other input? The 1.3. The answer is my output, right? So if I'm counting the number of sig figs in my input, I'm worried about what I'm multiplying together. So 2.67, how many sig figs do we see? 3 sig figs. And what about 1.3? That's 2 sig figs. All right. So then the last step here is we're going to compare, and we're going to report our answer to the fewer number of sig figs. So I'm going to compare 3 sig figs and 2 sig figs. Which number is fewer? 2. So that means I'm going to round my final answer here to 2 sig figs. All right, so everybody take a second, give me my final answer, put it in a box here. How would I report my calculation, this multiplication, to the correct number of sig figs? All right, so my second sig fig, I'm going to mark that 4. I'm going to round up. So this would become 3.5. Put it in a box. Okay? So we got to look at our inputs. Whichever input has the fewer number of sig figs, that's how many sig figs our answer is going to get rounded to. All right, we'll do a bunch of practice, but let's introduce the next one here, our next set of rules. Again, we talked about multiplication, division. We have a different set of rules if we have an addition or subtraction problem. All right, so these are now our addition subtraction rules. Okay, so first of all, I'm going to leave some space right here at the top, and I'm just going to put down an example. We're going to do, let's say, 9.5 plus 4.32. Okay, step one, let's do the math. Punch it into our calculator, we get 13.82. Cool? All right, but now we got to apply our sig fig rules here, right? This is our answer, but we got to report it to the correct number of sig figs. Okay, so, and you can, like, when you get really good at this, you can shortcut it, and you don't have to do it the long way here. But for right now, I'm going to teach you the long way, the proper way to do it, to make it so that you can really see what's going on here. And that is, we're going to rearrange these numbers to look a lot like when we were doing math back in elementary school. Right? When you were first learning to do math, what you did was you lined the numbers up, such as the ones were in the ones column, the tens in the tens column. So what we're going to do is we're going to line up these numbers at the decimal. All right, so I'm going to rearrange. I'm going to copy and paste here. And then I'm going to rearrange, stacking these numbers on top of one another, just like we were used to seeing back in the day. Okay? Didn't change the math at all. All I did was rewrite it. Again, now I have ones in ones column here, the tenths in the tenths column here, et cetera, et cetera, et cetera. All right? So now what we're going to do is we're going to mark the last sig fig in each input. All right, so given what we discussed about sig figs, put a bar over the last sig fig in those two inputs. All right, what's my last sig fig in 5.9? The 5. What about 4.32? The 2. All right, so I've marked my last sig fig in each one of those numbers. Okay. Now, whichever position is the least precise, meaning the furthest to the left, that's the position of the last sig fig in our answer. Okay, let me rearrange this a tiny bit. Okay, so what do I mean by that? All right, let's just try to follow the text of the rule here. My 9.5 has its last sig fig in what we would call the tenths column. And my 4.32 has its last sig fig in the hundredths column here. Well, which one of these is further to the left, the red or the blue column? The red. That would be what we would call the least precise sig fig, which means that my final answer is going to be rounded to that position, to that tenths column. So my final answer here, 13.8, put a box around it. Okay. Notice that if I had incorrectly applied the rules for multiplication and division where I was counting sig figs, I would have thought that my answer should only have 2 sig figs, when in fact I have 3 sig figs in my final answer. That's because addition subtraction, it's not a counting game. Nowhere did we go in and count sig figs. It was all about the position of those last sig figs in our number. Okay, so if I'm going to boil these two rules down to one word, because remember, we got 2 separate rules. They're not the same thing. We're going to try to keep them straight in our mind, which one's which. Multiplication division rules. This is all about counting your sig figs. Right? So if I'm going to boil this set of rules down to just one word, it's going to help me remember what I'm supposed to be doing. It's about counting the sig figs of your input. That's multiplication and division. Addition and subtraction, it is not about counting. It is instead about the position of that last sig fig. So if I'm going to boil this down to one word to try to help me remember what that rule is, I'm going to remember it's all about the position of the sig fig in my inputs. Okay, so depending on what your operation is, you're going to choose one of these 2 sets of rules, right? Multiplication, division, you got your counting rules. Addition, subtraction, you have your position rules. Cool. All right, let's do some examples of this, and then we'll move on. All right, so let's go through these here. I want to do this first one. I punched 4.6 divided by 0.539 into my calculator. It spit out 8.5343228, et cetera, et cetera. And I need to round this to the correct number of sig figs. How many sig figs am I going to round to? 2, because this input has 2, this input has 3. I go with whichever number is fewer, so that means my final answer here is 8.5. Okay? All right, 2.5 times 4.000. I punch it into my calculator. My calculator spits out 10. I'm done. No. Okay, what's the problem here? How many sig figs do I need to round my answer to? 2. To 2, because this input has 2, this input has 4, so that one wins. And that number is represented only has 1 sig fig. So what am I going to do? Add that decimal to the end. That's how we're going to indicate that that 0 is indeed significant. Okay? Let me just real quick tack another example onto the end here. Let's do 4.00 times 5.0000. All right, I'm going to tell you right now that if when I punch this into the calculator, my calculator spits out 20. Okay? How many sig figs do I need to represent that number to? This has 3, this has 5, so which one wins? The fewer number of sig figs. So I'm going to represent 20 with 3 sig figs. 20.0, absolutely. We just got to tack another 0 onto the end of there. We don't want to change the value, so we're not going to make it 20.1 and 20.9 or anything like that, right? It needs to be, the value still needs to be 20, but we do need to display that 20 with those 3 sig figs, okay? So be careful, your calculator doesn't know sig figs. Sometimes you will have to add zeros on or round some numbers off, as in our first case here. Okay. So now let's do this here, this addition. I'm just going to get rid of this. I'm going to go ahead and rearrange so that we've stacked it up. Okay. Punch this into my calculator. I get 17250. All right. Now remember, it's not a counting game anymore. It's about marking the last position in these inputs. So what am I going to mark as my last sig fig in 14,000? The 4. Why do I not count these zeros? There's no decimal point in that number, right? If there was, then all of a sudden I would count them, but there isn't. So I'm not going to count it. And what about in 3250?
3.
The 5 is my last sig fig. All right, so which one of these is my least precise position here? The red or the green? Which one's furthest to the left? The red. So that lets me know that I'm going to round to that thousands place here, or my final answer is 17. What's wrong? I did that whole change the value of the number business, right? It went from being 17,250 to just 17. So what do I have to do? I have to include those zeros, and I'm going to put a decimal on the end. Why not? Because I only want 2 sig figs, right? If I put a decimal on the end, now I have 5 sig figs. No. We need to put the zeros on the end so we don't change the value of the number, but we're not just going to tack a decimal on there. We're going to leave them insignificant, no decimal in that number. You could put it in scientific notation as well. That'd be perfectly fine. Yep. Importantly, in scientific notation, one of the nice things about scientific notation is the only digits displayed are always significant. So 1, 2, 3, 4, 1.7 times 10 to the 4. That would be perfectly fine as well to put that number in scientific notation. Importantly, I do have to represent it with only 2 sig figs in scientific notation. All right, now this one's a weird one here. 11,000 minus 1.25. All right, and let's just first follow our rules, and then I'll sort of take a step back and explain how this makes sense. Okay, so first of all, 11,000, what am I going to mark as my last sig fig? That second one there, right? No zeros because there's no decimal. What about in 1.25? What's my last sig fig? The 5. So before I even do any math, which one of these is further to the left, red or green? The red. All right, so let's punch this into our calculator. We get 10,998.75. All right, what am I going to round to? What am I going to mark as the digit I'm rounding to? The 0. So when I round this off, what's my answer? 11,000. And so everybody's like, what is going on here? We started with 11,000. We subtracted 1.25, and you're telling me our answer is 11,000. Okay? So how does this make any sense? So let's do another one real quick. Following this same logic, I want you guys to do one for me. We're going to take 39, and you're going to subtract off, what was it? 0.00 something something. All right, 0.000568. All right, so 39 minus 0.000568. I do my subtraction problem here, but according to my sig fig rules, I need to round to that ones position, meaning my final answer is 39. All right, similar to what we saw before. So again, how does this make any sense? What's going on here? So again, let's try to that was just blindly following these rules that we learned. Let's see if we can make some put some common sense to this, okay? So first of all, this wasn't really an arbitrary problem here. My house, again, up in Coarsegold, is located 39 miles that way, all right? So my house, 39 miles that way, all right? Now I'm gonna take one step back. Now how far away is my house? 39, right? Because those 3 feet that I just walked, or that 0.00068 miles that I just took a step back, is such a precise amount to take away from a number that was already pretty fuzzy, right? That 39 means I know it's somewhere between 38.9 and 39.1, but it's somewhere in that range there. If I take off this tiny this tiny precise number, it's not going to change what was already a really fuzzy value of that 39 miles, right? So again, what are these sig figs doing? They're representing a confidence. I don't know that it's 39.00000 miles. It's not exactly 39 miles, right? Again, it's somewhere between 39.1, or rather 38.9 and 39.1, somewhere in that range there, okay? And so that's what our rules of sig figs are doing, making sure that our answer does not over-represent the confidence in that number. When I take that step back, I'm not going to be like, oh yeah, now I'm 38.999483 miles away. No. I wasn't very confident with that 39 to begin with. Okay, so that's what we're doing with our sig figs. Remember, sig figs are all about the fact that in science, our numbers are measurements, and we cannot overstate our confidence or our precision in these measurements. We do so by displaying digits. The more digits you have, the more precise your measurement is. All right, and when we start analyzing these measurements, we don't want our answer to over-represent our confidence either, which is why we have these carrying rules. Okay, cool. All right, I'm gonna give you all just like a 10-minute shake it off bathroom break sort of thing, and then we'll jump into our activity that we got planned for the rest of the class period. Okay, for whatever reason you missed an example or you didn't get any notes correct or anything like that, you can come see me in this intermission here. All right, but again, we'll come back at 4 and we'll finish this off.
So do I just like add a class once you give me permission?
Correct. Yep. So basically, I'll know at the end of today how many spots are available. If your name on the wait list does come up, I'll send you an email and you'll add the course.
Okay, thank you.
Okay. If you're not registered for the course yet, you don't have access to Canvas, which means that you won't be able to complete the activity that we have planned for the back half of today. You'll have to do it once you get let into the Canvas course. Everybody else, you're going to stay and do these things for me, and then I'll let you go when you finish.
Okay, so do I go now or do
Correct. I just don't. I mean, you could stay and practice stuff on your own or whatever, but you don't have access to this activity that we're going to be doing.
Okay. So do I just miss the activity that will?
You will do it later on your own.
Okay.
Yeah.
Well, have a good one.
Yeah, absolutely. You too. Yeah.
So, okay, going back to the whole class transfer, for the whole transfer thing, you said go to the advising office, right? Or
Whoever your counselor should be able to tell you if you. So your concern is that you don't have the prerequisites for the course.
Yeah.
Your counselor should be able to tell you if you have the prerequisites for the course.
Okay. Do you know where the counseling office and stuff is at? This is like my first.
No idea.
Yeah.
Google it. That would be
Yeah.
that would be exactly what I would do.
Okay. Awesome.
Yeah.
Thank you.
There are specific STEM counselors, but let's see here. So I feel like I just